Hello there, everyone. This is legitimately my 22nd attempt at doing this. I counted. It's being recorded in this wretched manner with a laptop being held up to a computer screen because apparently my software isn't compatible with media site software. Anyway, moving on. I'm doing Chapter 7, Transient and Atmospheric Flows and Disturbances. Again. Sorry that the background is a little bit on the cat. This is what happens when your software is out of date. Don't let it do that. Okay. Sorry that the background is a little bit boring, but I kind of like it because it reminds me of the old sci-fi logo back in the glory days of Battlestar Galactica reboots before Sharknado ever graced the screen. Anyway, here we go. Okay, my table of contents. Okay, the impact of storms on the landscape, air masses, fronts, atmospheric disturbances, mid-latitude cyclones, mid-latitude anticyclones, minor tropical disturbances, easterly waves, major tropical disturbances, hurricanes, and localized severe weather are what I'm going to be covering. The impact of storms on the landscape. Storms are very dramatic phenomena. Even the mildest atmospheric change can influence our behavior. So basically, as far as atmospheric phenomena go, storms are the RuPaul. They are there to be seen and heard. They're there to be flashy. As far as changing our behavior, as soon as you see the sky clouding up and see that it's about to rain, you run inside to seek some shelter. The landscape can be affected just as easily. It can be significantly transformed in the short run if the storm's a violent one, like, branches getting blown around, what have you. And in the long run, the impact can be equally sinister. Soil erosion, uprooted trees, flooded valleys. But storms do also have long-lasting positive impact, such as vegetative cover diversity, plant growth, increasing size of lakes and ponds. So you're going to get stimulated vegetative growth because of the precipitation and nutrients that are getting down into the soil for the plants. And you're going to wind up with a better environment for, life in lakes and ponds. Okay, this is a palate cleansing slide. So, before we move on, if you need to, make peace with your gods or get in touch with your inner demons, go ahead and do that now. Okay, air masses. What are air masses? Air masses are variable parcels of air that are distinguishable from one another. Basically, air masses are formed by staying stagnant over an area of land or sea, and they just kind of stay stagnant over that surface, and then they take on the characteristics of those places, like their humidity, their temperature, stuff like that. As far as properties go, they're large. They're about 1,000 miles wide. They've got uniform horizontal properties such as temperature, humidity, and stability. Those are always going to be the same. And they have to be distinguishable from the surrounding air when it moves. You've got to be able to tell it apart. Okay, I just covered that. Air masses are generally formed with stable air. They have to be stable in order to be stagnant, so they're usually formed in anticyclonic environments, which we'll get to in a minute. Okay. Air masses have a two-letter classification system. The lowercase letter indicates moisture content. C for continental, which means it was formed over land. Maritime, which is humid, for M, and that means that it was formed over sea. It had more access to water, more moisture, and therefore, it's got more humidity to it. Uppercase letters indicate the source region. So you've got your polar source region, your tropical source region, and your Arctic source region. Then you've got your equatorial, I think that's how it's pronounced, source region. Ireland is usually very affected by the polar source region, but the thing is, by the time it reaches Ireland after going that large expanse of the Atlantic, it's heated up a lot. So they don't really get that bitter cold breeze that you would expect from a polar source region. So, lucky Ireland. Another palate cleanser. Okay, let's meditate. Think of a wide open field. full of technology that actually cooperates with you. Very, very, very relaxing. Oh, I think I skipped one. No, I didn't. We're good. Okay, fronts. A front is a boundary zone between two different air masses. So basically, it's a three-dimensional, narrow strip of air, and it doesn't really take on the characteristics of either of the two forces. Think of it as the neutral zone from Star Trek in between the Federation and the Romulan Empire. Basically, the two aren't going to impact the front at all. It's always going to stay the same. The concept of fronts was created by Norwegian scientists after observing the battle strategy for World War I. It was a really, 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 really stupid approach because trench warfare and then trench foot and gangrene and it was all bad. But anyway, one force would move, would advance, and the front would advance with them but wouldn't be affected, and the other force would be pushed back. The front itself never really affected. Fronts usually separate warm air from cold air, different temperatures, different densities. There are four primary frontal types. You've got your cold front, so your cold air advancing, your warm front, which is your warm air advancing, your stationary front, no advances of air masses at all, just kind of staying there, and the occluded front, where the cold air overtakes the warm air. Okay. Cold fronts. If you can see that protruding nose right there, wow, my hand looks huge in this. You can see that it's kind of pushing the warm air up. It's faster than warm fronts, and it lifts the warm air up ahead. There we go. And warm fronts are a gentle slope of warm air, and they usually, leave precipitation and clouds in their wake, and that's indicated by that red scalloped line right there. As you can see in both of these slides, cold air is always underneath the warm air. That's because cold air is more dense, so it's going to sink. Okay, stationary fronts. Neither the cold nor the warm air overtake or displace each other. They're just kind of, they're doing their own thing. And the occluded front is when a cold front overtakes a warm front. Okay, another palate cleanser. Alright. Puppies and kittens this time. Puppies and kittens. Cute little puppies and kittens that know how to work with technology way better than I do. Very relaxing. Okay, atmospheric disturbances. Different kinds of atmospheric disturbances, not just storms. I know whenever you hear a disturbance, you think of something that's going to be disruptive, something that's going to leave a little bit of destruction perhaps. But it's not just storms. Characteristics of an atmospheric disturbance. It's smaller than the general components of circulation, it's going to be on the move, it's not going to last very long, and the conditions that it brings about are going to be relatively predictable. Generally, we have a good idea of what they're going to bring about. Okay, mid-latitude cyclones. The most significant form of any atmospheric disturbance. They're responsible for day-to-day changes such as temperature changes, precipitation, and depressions, which are areas, pockets of really low pressure. Okay, some characteristics of mid-latitude cyclones. They're about 1,600 kilometers wide, which is about 1,000 miles for those of us who don't know how to use the metric system. All of America raises its hand in shame. It's a cell of low-pressure air, it's oval-shaped. It's moving in a counterclockwise circular movement. And the cool sector there's a cool sector and a warm sector. The cool sector is moving faster than the warm sector. The warm sector is kind of being whipped around by the cool sector that's chasing it. So the cold sector is always going a little bit faster than the warm sector. Got a diagram right there that shows that. Use the mouse this time, like a civilized person. As you can see here, the cold front is much closer to the warm front, and the warm front is kind of being whipped around as it's being chased by the cold front in a counterclockwise motion. Okay, weather changes with the passing front. Excuse me. The cold front, there's going to be a sharp drop in temperature. Whenever you hear the cold front is coming in, you think, okay, gotta bust out the jacket, gotta bust out the scarves, all that jazz. And then you're going to switch from a southerly ahead of the front to northwesterly behind it. And the pressure is going to drop whenever the front approaches, and it's going to rise as it passes. Whenever cold fronts come in, they usually bring in clouds and precipitation. It can be either rain or snow, depending on how cold the cold front actually is. And there's going to be similar changes with the warm front, but the thing is, the warm front doesn't really have the same power as this. Its changes are going to be much more understated. Okay, movements. Basically, they have nomadic features. They are the Bob Seger of, atmospheric disturbances. They're always on the move. There are 4 kinds of movement. The whole system is moving as one major disturbance across the westerlies. It always sticks together. It's not breaking off into separate pieces. It's got a cyclonic wind circulation, so it's moving around in a big old circle. The cold front is advancing faster, and the warm front is advancing slower, which we saw that in our diagram right there. Okay, cyclogenesis. I love the word cyclogenesis. I capitalized it because I think it's so cool. Personally, I think if the band Genesis had gone with the name Cyclogenesis, they would have had a little bit more longevity, and Phil Collins would no longer be eating out on No Reply at All. Okay. A cyclone will typically go from inception to maturity, so from birth to full force, in about 36 days. From maturity to dissipation, so from full force to death, it'll take about the same time, 36 days. Eventually, the cold front takes over the warm front, and the cyclone is going to die a horrible, miserable, lonely death. Fun. An occluded front is going to form as a result of this. About 6 to 15 of these are going on at any given time. I'm very sorry about the screen shaking. That's my hand, and yeah, I'm very caffeinated. Okay, mid-latitude anticyclones. These are very extensive migratory high-pressure cells. So if you remember, cyclones are very low-pressure cells. This is the exact opposite. They typically are larger than a cyclone. They're moving from west to east. They contain no fronts, so the warm air and the cold air aren't fighting each other or chasing each other. There's no conflict. You're going to have a lot of clear, dry, really pleasant weather as a result of these, and they tend to be more stagnant. They've got more of a stagnant tendency than cyclones actually do. They're more willing to hang around for a while. Okay, the relationship between cyclones and anticyclones. Got a little picture here for you. They're alternating irregularly, and they can occur independently, but they usually have a functional relationship between the 2 of them. So if you see here, the cyclone is moving, in a general that way direction, and the anticyclone is following behind it. So we've got a little bit of, unpredictable weather as we've got these 2 fronts coming together. And the anticyclone is following up with some nice weather because it's nice like that. Okay, minor tropical disturbances, easterly waves, oriented north to south. They're long but weak migratory low pressure systems. It's basically just a chain of really mild thunderstorms. It's a common kind of tropical disturbance, happens all the time. Most will weaken out and die in the ocean, but a little bit less than 10% do have the potential to become hurricanes. Before the wave, you're going to get fair weather, and you're going to get thunderstorms afterwards. Major disturbances, hurricanes. They're intense, low-pressure disturbances, much smaller than mid-latitude cyclones, and they develop from low-pressure perturbations called tropical disturbances. Tropical disturbances can range from a tropical depression, where the wind is less than 33 knots, to a tropical storm, which is all those alphabet storms, from about 34 to 63 knots, I think. And the hurricane is 64 knots or 74 miles per hour and above. It pulls in warm, moist air, so that kind of brings in a lot of condensation, and it leads to instability. I've got a point for that right there. They've got prominent low pressure centers. That's the eye of the storm. It's very low pressure. And it's got a steep pressure gradient, which means that the wall of the eye is very, very high pressure. It's a very, very quick change, and that's creating a little bit of chaos. They're very high energy. A mature hurricane, it can produce in one day the same amount of energy that all the electrical utility plants in the United States can create in 1 year. So, yeah, little ball of energy and destruction. Got a little picture right there. You can see the eye of the storm in the middle, that little black dot. That's a place of actually really peaceful weather. The eye of the storm is about 10 to 25 miles wide. It originates over warm oceans in the tropics from tropical disturbances, which we talked about just a second ago. Okay, localized severe weather, thunderstorms. It's a violent convective storm. It can have precipitation with it, but usually it's just, usually it has precipitation with it, but it doesn't need that to be classified as a thunderstorm. It just needs the thunder and lightning. Lightning is created whenever really positively charged ice particles are pushed up by warm air, and negatively charged ice pellets drop lower towards the cloud. And at the bottom of the cloud, it's very, very negatively charged. And as it gets closer to the positively charged ground, it builds up static, and eventually lightning happens. The boom that we hear from thunder is basically the air expanding to make room for these hot flashes. It's displacement, and air doesn't like it, so it makes a loud sound to let everyone know about it. Tornadoes are a deep, low-pressure cell. They're the most extreme pressure gradients known, very, very low pressure in the middle and very high pressure on the outside. Vertical wind shear creates rotation with a horizontal axis, and then it gets tilted up by a thunderstorm updraft. They're rated on a scale from F0 to F5, and I had a map that I should have put on here, but basically the United States has the most tornadoes out of anywhere in the world, and Ireland has virtually none. So yeah, Ireland's really, really lucky. Okay, I really hope that I actually get to upload this one, and I'm very sorry that it was recorded so ratchetly. Thank you all very, very much. I'll see ya.